Hi, I'm Laura Blecha at the University of Florida, and today I'd like to tell you about some of the work my group has been doing to model the Illustris population with cosmological simulations. And I'm specifically talking about supermassive black hole binaries in merging galaxies. So I'm going to be talking about three fairly distinct topics. I wanted to give you a roadmap so you know where we're going with this. The first topic is supermassive black hole binary spin evolution, which my student Mohammad Sayeb has recently developed models for and published a paper on to address the questions of how gas and gravitational wave driven evolution drives spin alignment or misalignment, and whether we expect as a result to see large gravitational wave recoils and even precessing waveforms. The second topic is the connection between galaxy mergers and black hole fueling, which is uncertain and actively debated, and is relevant for LISA because it affects our ability to use observations of AGN to understand the underlying population of inspiraling black holes that we'd like to use for making gravitational wave predictions. And so I will refer you to the talks by Aklant Bhowmick, my postdoc, and my student July Thomas about that, in addition to the talk by Mohammad Sayeb about binary spin evolution. And then the third topic I'll address is the impact of black hole seeding on LISA sources. So we don't know how black holes form in the early universe, and this is thought to have important implications for the LISA population that we observe. And so we're currently developing gas-based black hole seeding prescriptions for AREPO cosmological zoom simulations to address this question. So this movie is showing the evolution of several different quantities in the IllustrisTNG cosmological simulation. So IllustrisTNG is a large volume, high resolution simulation run with the AREPO magnetohydrodynamics code. So AREPO includes magnetohydrodynamics as well as gravity, and a suite of subgrid models for physics that can't be resolved directly, such as stellar evolution, gas enrichment in the ISM, and stellar feedback, as well as black hole physics such as fueling, feedback, formation, and merger. So you can get a sense of the scale of simulations and the types of physics that we're able to include from these simulations. If we focus on this stellar density plot here, you can see that there is this galaxy that has recently undergone a merger. So we'll use that as an example for how we model black hole binary evolution using these simulation data. So again, we can't resolve this directly, but we develop post-processing models for black hole binary in-spiral timescales and spin evolution. Kelley has developed in-spiral models in a series of recent papers, and then my student Mohammad Sayeb, as I mentioned, has developed this new spin evolution model. And so what does that consist of? Well, on larger scales, spin evolution is likely to be dominated by the interactions with surrounding gas. Specifically, if the black hole binary is embedded in a circumnuclear gas disk, then the black holes are likely to have their spins aligned on a fairly short time scale by gravitational torques from the disk. But if there isn't a coherent thin disk with a well-defined angular momentum axis, if instead, for example, gas streams are infalling along continually different directions, then we might be closer to a chaotic accretion scenario where spins would tend more towards a random distribution. And this is also what you would expect if there simply isn't very much gas at all in the galaxy nucleus. And so stellar dynamics is instead dominating the n-spiral. So if the black holes are misaligned when they enter the gravitational wave dominated phase, then they will undergo gravitational or general relativistic precession in this gravitational wave phase. So the spin evolution in this phase depends on the binary parameters, but in general will be dominated by the primary black hole, the more massive black hole. So as I said, my student Mohammad Sayeb has developed this model in a paper that we recently submitted. And I encourage you to check out his talk for all of the exciting results that he will describe about this recent work. I'll just highlight that indeed we do find that a significant population of misaligned spins should occur in the gravitational wave phase, even with conservative assumptions, and also that we expect to see, as a result, a tail of large recoil velocities above 1,000 kilometers per second. And we also find indications that strong GR precession might persist down to merger in some cases, which, if the amplitude of precession is high enough, could result in a precessing waveform signature, something like this, that could be observed. So again, I'll refer you to his talk for more details. The next topic is the role of galaxy mergers in fueling black hole growth and the AGN that we observe. So, as I said, the connection between galaxy mergers and AGN is uncertain, and this likely has a lot to do with the roles of obscuration, dust obscuration in merging nuclei, as well as the dependence on merger stage and AGN luminosity in determining the exact quantitative relation between mergers and AGN. So on the left here, you see a set of plots showing obscured AGN in merging nuclei from recent work by Koss et al. And on the right, these panels here show a set of simulated images from obscured AGN and merging nuclei from a recent galaxy merger simulation of mine. And so the idea is that we would like to be able to quantitatively compare these in a robust way that allows us to use electromagnetic observations of AGN to constrain black hole binary and spiral timescales and make gravitational wave predictions. So my postdoc, Aklant Bhowmick, has been working on using IllustrisTNG data to study black hole pairs and multiples and their AGN fueling. We've recently submitted this paper. It's available in the archive. And as is the black hole spin evolution paper I should have mentioned. So again, I encourage you to check out Aklant's talk for full details. He has a lot of very interesting results. And I'll just highlight that indeed he does find that these pairs and multiples are on less than 100 kiloparsec scales are several times more likely to contain luminous AGN than random pairs, which you can see here parameterized by this excess over random pairing, which increases towards high accretion rates or high Eddington ratios in this case. So yes, I encourage you to check out his talk for full details. My student, July Thomas, has studied a similar question, but from a different perspective. So she's utilized the availability of the very high time resolution ancillary black hole data from the TNG simulation to study merger-driven growth in a much greater detail than we can from snapshot data alone. So just to give you a sense, from this top plot here is showing the accretion rate versus time before and after a merger event. And the red dots here are meant to indicate typical snapshot resolution in the TNG simulation, while the blue curve shows the full accretion history for this merger event from this higher time resolution data. So you can see that it really is a much richer data set that allows us to probe these questions. And so again, I certainly encourage you to check out her talk for full details. She has lots of exciting results. And this is just one of several plots highlighting that mergers are indeed an important fueling channel for select subpopulations of black holes. So the third topic I'd like to address is the formation of black holes in the early universe. So we don't have really any empirical constraints on this. We know that massive quasars exist by redshifts of 6 and 7. And so these seeds must have formed very early on. But we don't know, for example, whether they formed at low masses from the remnants of the first population 3 stars, which would require them to grow very rapidly in order to reach the supermassive regime by redshift 7, or whether they started out with larger masses, say from the direct collapse of atomic cooling halos, which makes it easier for them to grow to large masses, but may require fine-tuned conditions to occur. And then we might end up with an intermediate case where, say, a star cluster forms and undergoes runaway mergers if it's embedded in a dense gas cloud. So we're parameterizing these combinations of models with criteria based on the gas properties in high redshift halos. Specifically, putting constraints on the gas density that has to be above the star formation threshold, and on the gas metallicity in the center of the halo as well, that it must be below a certain low metallicity threshold. And then we also require a minimum halo mass and optionally a seeding probability less than unity. So that as of now, those are the criteria that we have in these models. And then we can tune these different criteria to mimic whatever flavor of seed model we are trying to create. So this is work that's being led by Aklant Bhowmick, my postdoc, as well as my student Analis. And I should say that this work is very preliminary, so please take everything here with a big grain of salt. But the top plots here, which are meant to be illustrative, show the gas density and metallicity in a high redshift Z of 7 forming massive halo. And the green dots here show the black hole seed locations, where the size of the dots is scaled by the black hole mass. And then a similar simulation that was run to lower redshift, we've taken and plotted the black hole mass stellar mass relation at various lower redshifts. And you can see that the models from these Zoom simulations are the gas-based models are a little above the halo-based model for these particular gas-based seed models we're showing here, which are close to, but also a little bit above the Megorian relation shown in the gray dashed line here. And then all of these are substantially above the Rhines-Volontaire relation, which has a lower normalization. So as I said, this is work in progress. Please stay tuned for further updates about that. And then the very last thing I'd like to highlight is some other ongoing work that is in early stages to develop other new subgrade black hole physics for AREPO. So part of this involves using a super Lagrangian grid refinement scheme, which we're implementing for multiple black holes in cosmological simulations. And so that's illustrated here. The top plot is showing zoom in of a black hole with no extra refinement, whereas the bottom has this super Lagrangian refinement implemented. And so you can see the highly specific regions we're able to refine in greater detail. And then we're also using the SMUGGLE ISM model for an explicit multi-phase ISM, which was recently implemented in AREPO by Marinacci et al. And so you can see the rich structure and higher gas densities that are achieved here versus the traditional Springland-Hernquist effective equation of state model, which is commonly used in these simulations, including IllustrisTNG. So again, that's early stage work in progress, and that's being led by my student Aneesh Sivasankaran. So stay tuned for further updates about that as well. So in summary, I'll leave you with my overview slide to remind you of what we've covered. We have newly implemented models for black hole binary spin evolution, and which you can hear more about from Mohammad Sayeb's talk. And we've also been quantifying the connection between mergers and AGN in IllustrisTNG, which you can hear about from Aklant Bhowmick and July Thomas' talks. And then I talked about what we're working on currently to develop new black hole seeding models and other black hole physics models for future AREPO simulations. Thanks for your attention. Bye.